starting back here. Okay. All right, so can we go ahead and hit those lights? So I think we are getting to the point with Newtonian mechanics where you guys are actually starting to see the pattern. And we're going to go ahead now and, last time we talked about horizontal motion of a cart in the presence of linear air resistance. And today we're picking up from that. And we're going to talk about a vertical motion problem with linear air resistance. So we're going to have a question. It will relate to vertical motion. Okay. All right. So I'm going to imagine that I have taken an object and I have thrown it down with some initial velocity v naught. So here's my object, it's a ball. I threw it down with some initial velocity v naught, which is, in my, I'm not going to use the standard coordinate system. I'm going to go ahead and let down be the y-hat direction for this particular problem. Now and then you want to do that, so I'm going to model that for you. All right. And in this case, a free body diagram for this object includes its weight, in this case in the positive y direction, and its air resistance, which I have drawn opposite the direction of the velocity. Okay. In this case, it's a one-dimensional problem. So I have the sum of all y components of forces is equal to mass times the y component of acceleration. And when I plug in on the left-hand side the sum of all y components of forces, remembering that I've called down positive, I get mg minus bv. Okay. And now that I see that I've got a force here that is proportional to velocity, the trick to remember is that in that case, and by the way, I'm going to go ahead and do a subscript y on that. The trick to remember with this problem is that we write our acceleration not as a second derivative of location, we write it as the first derivative of velocity because velocity appears on this side. All right? Okay, that is the trick. All right, so let's go ahead and consider, I've got my my equation of motion that I'm going to have to solve. But there's an important variable that will be in my final expression, because I just know it's coming. So let's discuss it, and it's terminal velocity. So I'm making a little bit of an aside here. In the end, my object that I have thrown downward, all right, will come to a final velocity. And at that point, its acceleration will go to 0 because it will continue to have that velocity. All right? So we'll just say as time goes to infinity, I know that mg minus bvy will be equal to mass times acceleration, except at that point, the acceleration will have come to 0 because it will have found some final value of velocity. This is just from observation that we know that this is the case. All right. And in that case, we call Vy, we give it a special name. We call it the terminal velocity. So we call that V term. So now I have the expression mg is equal to b V term. And V term is equal to mg over b. All right. And that's our expression for terminal velocity. All right, so there's the end of my aside. Let's just pick it right back up from here. Boop. Is that big enough up there for you guys to see, or do I need to zoom in a little bit? I feel like I'm normally zoomed in more, but are you guys all right with this? Cash, are you okay? Can you see? All right. Okay, so let's go ahead then with that in mind. So I've got, I'm going to rewrite my expression for Newton's second, and I'm going to flip it because I like to have my derivative all alone on the left-hand side of the equal sign. So I'm just going to flip it first. mvy dot is equal to mg minus b vy. Okay. And I notice that if I divide both sides by b, and let me tell you actually why I'm doing this. So what I have here is an issue. I have a problem because I have a variable over here, vy dot, and then I have this other thing over here that says vy, and then I have this other constant here, and I don't know how to solve it. So what I'm going to do is I am going to write vy dot. I'm going to simplify this. So I already know where we're going, so I'm just going to go ahead and show you how I do this. So I'm going to imagine I want to divide both of these guys by b. And in order to keep my equal sign holding, I have to multiply by b out front, or in this case, out back. Are you all right with that step? All right. There's a couple reasons that I did this. But the number one reason is that I wanted to get something linear in v over here to be on the right-hand side, to be my variable on my right-hand side. So what I've got now is v term minus vy times b, which is okay. I wanted something linear, but I'm going to want something linear in positive vy, and you'll see why in a second. So I'm going to pull a minus sign out front. Then I'll write that as vy minus v term. Okay. Now the reason that I did that is that I want to do a change of variables. I want this object here to be my variable, and in math they called it u. I'm not going to talk that much about it, but if my variable were to be, I feel like I've completely gone off my notes, but I think I'm all right with that. I think it's all right. So if I were to allow or assign u is equal to vy minus v term, where v term is a constant, it's just the mass of the object, acceleration due to gravity, divided by the linear drag coefficient. All right? So this guy here is a constant, has no time dependence. If I do that, then du dt, also known as u dot, would be equal to, well, the derivative of the first term, dvy dt, plus the derivative of the second term, which is 0. So that's nice. I'm going to go ahead and make that change of variables. And then I'm going to want, so let me just go ahead and make that change here. So I've got mass times an object, which is vy minus v term, time derivative. So that time derivative is over the whole thing, the whole argument of that's inside those parentheses. Because I just found that in this case, the time derivative of vy minus v term is equal to dvy dt. Are you guys okay with that? Sam, are you all right with that? Okay, cool. All right. So then I have is equal to minus vy minus v term. Okay, I know how to solve that one. I'm going to divide both sides by m. So I've got this thing. And now, if I had, you know, this is a differential equation. So now and then you have a differential equation where it's like, you know, your variable dot dot, like x dot dot, is equal to some function of time, and you can just integrate it twice to get x or whatever. This isn't one of those. This is one of those differential equations where I have to guess the solution. I can't just integrate my way out of this one, right, Logan? So I'm going to have to guess the solution. We've seen this a couple of times, but it takes a little while to see the pattern. But in this case, I've got u dot is equal to minus b over m times u. So what that tells me is that u is equal to a constant times e to the minus b over m times time plus a different constant. All right. So what I get as a result, and if you prefer to look at it like this, u dot is equal to minus b over m times u. All right. Then what you get is that u must be equal to a constant e to the minus b over mt plus a second constant. That's the general solution. Because when I take my derivative, what I get is minus b over m times this thing back. All right. Is everybody okay with where this came from? All right. And if you're not, just email me and we'll have some office hours and talk about it. All right. So what I have here now, I'm going to make my substitution back and notice that my u was vy minus v term. Now, the way that I figure out what these two constants are is boundary conditions. I get A and B from my boundary conditions. My boundary conditions on time, on my variable. So that means there are two boundaries for time. There's this initial time where t was 0, that the velocity, that Vy was equal to minus V naught y. And then I've got this other case where time goes to infinity. That's the other bound on time, in which case my velocity is equal to my terminal velocity. So I just apply those two boundary conditions and I figure out what they must be. So in the interest of going a little bit faster, I'm going to wave my hands. As t goes to infinity, Vy will be equal to v term. That's one boundary condition. Now that boundary condition gives me, well, Vy minus v term as t goes to infinity must be equal to 0. My first term on the right-hand side automatically goes to 0 because of its time dependence, and my second term must also be equal to 0 to meet that boundary condition. And my second boundary condition is when t is equal to 0, Vy is equal to v naught y. V naught y is equal to Vy, but I meant to write Vy is equal to v naught y. Okay. So I make that substitution, and I get, plugging in for Vy, I get v naught y minus v term on the left-hand side is equal to a times e to the 0, because t was 0. So a times 1. All right. So this guy here, also known as 1. All right. So that tells me that a must be equal to v naught y minus v terminal. So I get my final expression. Okay, so I get that expression. And what I want is I want to know v is a function of time. That's the thing that I am solving this differential equation for, is my variable Vy. So I get Vy is equal to v term plus v naught y e to the minus b over mt minus v term e to the minus b over mt. And I'm going to gather up everything that's multiplying v naught y, which is just one term, plus v term times the quantity 1 minus e to the minus b over mt. That's it. So now I have a solution for velocity as a function of time. And yeah, your author, of course, is going to write this in terms of time constant because he really likes time constant, which is fine. E to the minus t over tau plus v term 1 minus e to the minus t over tau, where tau is equal to m over b. All right. So now I have solved the differential equation that I got from Newton's second law. And the thing that it gave me was velocity as a function of time. If I want to know acceleration as a function of time, I can take the derivative with respect to time. This question, for some reason, doesn't do that, but that's something you could do. And if you wanted to know location, you can do an integral with respect to time. So let's do that. So this is our expression for velocity as a function of time. Great. So now I'm going to rewrite it so that I can do an integral on both sides. You know, I'm going to take this expression because it's easier to integrate. So I'm going to take v term plus v naught y minus v term. Am I off the page? I'm sorry. So I'm backing up to the expression from this line just because it'll be easier to integrate, save me a step. And I think actually your author is going to do this in terms of tau again, isn't he? Yeah, he sure likes his tau. I'm sorry. Change that to minus t over tau. Okay. All right. So now if I want to know location as a function of time, I integrate both sides from over time, over dt from 0 to t. And I'm going to go ahead and break the two terms out. All right. And so what I have on this side is dx dt times dt from 0 to t, which gives me x at times t minus x naught. We can go ahead and make our coordinate system that, I'm sorry, that should be y as a function of time, minus y naught. That was dy dt, not dx dt. And we'll go ahead and choose our coordinate system such that y was equal to 0 at t equals 0, so that term can be 0. And then on the right-hand side, how about you guys go ahead and get the expression for the right-hand side? term is a constant. So, you gotta change, yeah. Yep. Jacobians.
There we go.
Yeah. So, Ryan, talk to Logan. That one, that one. Yeah, that's fine. What's your where's your calculator?
I didn't bring it.
Oh, well then.
I didn't think I needed it.
Oh, no, that's fine. All right.
My portable math CAD.
You know, that brings up a good point. So you've got a portable math CAD thing, really?
Well, it's an old calculator that does differential and.
Because I have a numerical problem that I'm gonna think about assigning for the next set, but I need to get MathCAD set up on all your school accounts. Does anybody have MathCAD already on their school accounts?
Yeah, I think most of us do.
Yeah, I've actually got mine on my laptop.
So I can go ahead and assign it. All right, well, that's coming Monday anyway. I can't remember the number, it's from chapter 1. All right. All right, so let's go ahead and solve the right-hand side. So we've got terminal velocity, which is just a constant, times the integral of dt from 0 to t, which gives me t minus 0. Okay. And then I've got this thing here that I have to think about. The second term here, it's a constant that I'm going to sort of pull up front, v naught y minus v term. Both of those are constant. Initial velocity and terminal velocity are both constants in this problem. So now I have an e to the u du that I want to get. I don't currently have it. In order to get it, I have to get what's called the Jacobian. I have to have this thing be du, which means I have to multiply by a minus sign and a 1 over tau, which means in order for my equal sign to hold, I have to multiply by a minus sign and a tau out front. All right, so I've got this negative tau, and now I've got the integral of e to the u du from 0 to t. So what that's going to give me is e to the u that I have to evaluate from 0 to t. Are there any questions about that?
I did 1 over tau, that's what I did wrong.
Yes. Yeah. Are there any questions about that, though? Is that something that you guys, if I turned this over and had you do it again, pretend that we did it fresh, could you do it? Yeah. Okay. All right. So when you come in on Monday, be ready to just maybe practice this step from here to here a couple times over the weekend, just to make sure that you can solve this problem. All right. Okay. All right. So what we've got for location is a function of time. Is v term t, and I'm going to take, because I know this final expression here is going to give me an e to the minus t over tau minus 1, and I'd prefer to have it as 1 minus, so I'm going to go ahead and say plus v naught y minus v term times a positive tau, just so that I get the expression I want in the end, which will be 1 minus. So I'm going to evaluate from here to there, because I got a minus on it, e to the minus t over tau. And this is the object's location as a function of time. So I know velocity and location is function of time. I could have gone ahead and integrated this and gotten taken a derivative of this object and gotten acceleration as a function of time, but we all know how to do that, so we're not going to do it. All right, so are there any questions about this problem at this time? All right, so let's come back to this velocity here as a function of time that I got here. And let's think about it and make sure that it sort of checks out physically, because that's kind of a complicated function of time. It is indeed correct, but it is a little complicated, and we might want to be able to compare it with something that we learned about in a previous class. So let's consider if Vy naught were 0, if it was dropped from rest instead of thrown downward, then this first term would be equal to 0, and Vy as a function of time would just be equal to V terminal times 1 minus e to the minus t over tau. All right? And I'm sure that I wouldn't want you to have memorized anything from 242.50. There's nothing to memorize in 242.50 except Newton's law and the conservation laws. Because now that you know this, you can rederive every single expression I ever showed you and put a box around, right? Maybe you're not seeing it yet, but we'll get there. Anyway, so this does happen to check out with the expression that we saw in 242.50, but there's no point in having any rote memory of anything like that, because you could just rederive it in a few lines. And what that means, what this function looks like when I plot it as a function of time, is that it heads exponentially to this terminal value, V term. And the curve will be something like that. I should have made it more of an exponential looking thing. But anyway, all right, so what happens is that after, and here's, by the way, right around here is my 1 tau. And the way that I know that 1 tau is around there is that at that point, it's basically 1 over 2.73, sort of 2/3 of the way to its final value. 1 minus the 1 over 2.73 to its final value. When t is equal to tau, I've got 1 minus e to the minus 1. 1 minus 1 over 2.73. All right, so it's like 1 minus a third, about 2/3. So when I'm about 2/3 from where I was at a previous time, when I get about 2/3 of the way to my final value from that value, then I'll know one time constant's gone by. So again, from here, I'm going to say, here's about another time constant, because this was what it was before, and now it's about a third of that. Okay? All right. So yes, we get an exponential curve that's heading to a final value. All right. And that does agree with the system that we dealt with before. Now, before we were never able to solve a system as complicated as this, where I started with an initial velocity. We're already in new territory there. All right. So now I think we're finally ready, unless there are any questions about that. I think we're finally ready to talk about the two-dimensional problem with linear drag. So let's do, what were we doing before? Vertical motion with linear drag. So now we're going to do a two-dimensional problem. And again, I'm still going to have a linear drag term. All right. So we're kind of going back to that place where we were last time, where I had us put a pin in it, the two-dimensional problem. I'll just remind you where we were last time when we took a little break. So we were talking about an object that had been thrown such that it had an initial velocity v naught. Neither straight up or down. This object will not go either straight up and down or purely horizontally. Okay? So in this case, if I were to draw a free body diagram for this object, its weight, mg, will be directed down. So its direction is included in the arrow. So this is just its magnitude labeled on here. and its drag force will be opposite to the velocity, and it will, so the direction is contained already in this arrow, and it will have a magnitude that is equal to BV. All right, so it's the drag force is equal to BV in the negative V hat direction, and that's what I've drawn on here. So now I'm going to choose a more conventional coordinate system and solve the system. All right. So for this system, I need to do Newton's second law in both directions. And let's go ahead and do it. So this is going to be a good chance for us to show that we, to do this math one more time and get it into our muscle memory here. All right. Now, sum of all forces in the x direction, meaning sum of all x components of forces. I only have one force with an x component, and its x component is minus BV. And by the way, this minus sign takes care of itself in terms of sign convention. I have chosen V to have both positive x and y components, but I've chosen that so that the expression that I get in the end will work for all conditions without loss of generality. All right? Because if the x component of V is negative instead of positive, our final expression will still hold. All right? So I've got minus BV, BV's x component. So minus b times the x component of v is equal to m. And now that I see that I have velocity on my left-hand side, I'm going to do my trick, where I write my right-hand side in terms of velocity as well, so that I've got a differential equation that is soluble. I'm going to have you guys solve this one for Vx as a function of time right now. Try not to look back at your notes. Try to do it fresh so that you can sort of get some learning out of it. So solve it for Vx and then solve it for x as a function of time. Just use what's right here, okay? Take it on from here. Pressure yourself. We have to guess a solution because we've got V dot on one side and V on the other. We have to guess the solution.
Oh, they'll probably collect that anyway, you know?
Yes, that's fine. So now you have, you just want to get, so you've got this alone. So go ahead and, yeah, keep writing. And then once you get it all on the left-hand side of your derivative, stare at it, have an epiphany. So we need, there's, we need also that. So we need a function whose with respect to time, proportional to itself. So you're meeting your boundary conditions right now? Very good. Yeah, looks good. Is T goes, yes, that's correct. It's all right. Yeah, I know. It's if you're banging your head on your desk so bad that you got a bloody spot, you can look back. All right, I'm going to go ahead and work this puppy. I'm going to get this guy all alone and put him on the left-hand side of the equal sign. So I've got Vx dot. Watch me close and tell me if I've got errors, please. Minus B over M Vx, which means that Vx as a function of time will be A e to the minus B over mt plus B. Just staring at that and saying, I need a function whose derivative with respect to time is equal to some constant times itself. And this is the one, that's the only one I got that does that. Cosine doesn't do it because it gives me sine back. So yeah, that's the only one. All right. Now, I've got Vx as t goes to infinity must be equal to 0. And that yields B must be equal to 0. Because when x goes to infinity, Vx is equal to A times 0 plus B. So in order for that to be 0, B must be 0. I've got Vx when t was equal to 0 was equal to V naught x. That's the x component of the initial velocity. That yields Vx at 0 is equal to A times e to the 0, also known as 1. So A is equal to V naught x. All right, so I've got Vx as a function of time is equal to V naught x e to the minus B over mt. And if I want to find x as a function of time, so because we're done here, that's velocity is a function of time. So now if I want to find x as a function of time, I'll take that expression and I'm going to integrate both sides from 0 to t. So 0 to t times dt. All right, now I'm going to, this right-hand side, I have to have e to the u du, which means I have to turn dt into du, and I do that by multiplying by negative b over m. In order for my equal sign to hold, I must multiply outside here by negative m over b. And what I get is x as a function of time minus x naught. Let's go ahead and choose our coordinate system, so that is 0 is equal to negative m over b times v naught x times e to the minus b over mt from 0 to t. This time I'm not going to use the tau convention that your author uses. We should be fine without it. Same deal either way. And this, when I evaluate this, it's going to give me an e to the minus b over mt minus 1. I'm going to want that to actually be the other way around. So I'm going to write that as plus m over b v naught x times 1 minus e to the minus b over mt. Which tells you that as t goes to infinity, delta x will go to mv naught x over b. Exact same result that we got for the cart. Now, for the y part. I got a couple minutes, so I've got a minute and I'm going to use it. Because this is set up a little bit differently from your last one. And, oh, grass. All right. So let's take a look at this. I need to plug in for in my y direction, and I've got, for some of all y components, because I now am calling up the positive y direction, I've got minus mg minus bvy is equal to m, and I'm going to go with vy dot here because vy appears in my expression on my left-hand side of Newton's second, so I'm going to use my right-hand side in terms of vy as well, so that I get a differential equation that I can solve. All right, so I think what we should do at this time, because this is lovely because it's going to give you a slightly different expression than the last one, sign differences and things. So sign differences is all that you'll get, but anyway, it'll be worthwhile because this is a place where you can practice your chops. All right, so over the weekend, solve that right-hand side. When I come in on Friday, I'm just going to zip through it at the very start and then continue on with quadratic stuff. All right. Is it Friday? It's Friday, right?
It's Friday.
Okay, all right. Have a good weekend. All right. Hello. Let me turn off the mic up here before we talk. Hold on, get this thing recording.